Hello everyone, welcome back to another lecture of machine design. Today we're going to go over this lovely problem. A flat leaf spring has fluctuating stress of sigma max equals 360 megapascals and sigma min equals 160 megapascals applied for 8 times 10 to the 4 cycles. If the load changes to sigma max equals 320 megapascals and sigma min equals negative 200 megapascals, how many cycles should the spring survive using the Goodman criterion? The material is AISI 1020 CD and has a fully corrected endurance strength of SE equals 175 megapascals. We are only going to do part A of this problem since Manson's method is rarely used, so it won't be tested on the exam. So a flat leaf spring, we have to know what a flat leaf spring looks like. So let me Google and show you guys. So this is what a flat leaf spring looks like. Um, and it's basically a spring except it's flat, but it stores potential energy. So hopefully that helps you guys understand the problem better. So what is Miner's method? Miner's rule states that D is equal to the sum of small n I over capital N I. So Miner's rule essentially says, like, for instance, like we have a first loading that produces this type of pattern, and a second loading that produces this type of pattern. And this is the first one is N1 cycles, and the second one is N2 cycles. And in this problem, we are given N1 and we need to find N2. So Miner's rule for this particular problem, the sum of Ni over Ni equals to 1. So we will use that. In the context of this problem, Meyer's rule means that since the sum of Ni over Ni is equal to D, here N1 over N1 plus N2 over N2 is equal to 1. So we know that what are our givens? We are given that N1 is equal to 8 times 10 to the 4 cycles. And we want to find N2. How many cycles should the spring survive? So we want to find N2. And we're also given that sigma max for cycle 1 is equal to 360 megapascals. And for cycle 2 is equal to 320 megapascals. And we're given that the fully corrected endurance strength is SE equals 175 megapascals. So we're also given the ultimate tensile strength because we are given that the material is AISI 1020 CD, so cold drawn. So we can find the ultimate tensile strength from that information. Um, so basically we have a graph over here and AISI 1020 CD, so cold drawn, is going to be equal to this one. So oops, okay, wait, hold on. Yeah, it's equal to 1020 and then cold drawn. And we want in megapascal, so the tensile strength will be 470 and the yield strength will be 390. So 470 and 390. So Alma tensile strength will be 470 megapascals. And then the yield strength will be 390 PA. All right. What else do we know? Well, we know the boundaries of sigma x and sigma min for both first and second cycle. So now our next step is to find N1 and N2, since those are the things that we can find. So what is the expression for N again? As we see over here, N can be expressed as the completely reverse stress over A to the power of 1 over B. And how can we find the completely reverse stress from as a function of in terms of sigma A and sigma M? We have this equation over here for the Goodman that reverse stress sigma AR is equal to sigma A over 1 minus sigma M over the ultimate strength. So the two equations that are of interest to us are going to be these ones. Uh, this equation over here and this equation over here to find n. And once we find the two n's, we can isolate the lowercase n2 that we want to find. So here I put both of the equations here so that it will be easier for us. So we first have to find the sigma I and sigma M. But before even doing that, we have to find A and B. So A is given by what? As we see over here in this equation sheet that I created, A is given by F times SUT, which is the ultimate tensile strength, over SE. And then B is given by negative 1/3 log of F times the ultimate tensile strength over SE. So these are the two equations that we'll be utilizing as well. So we'll be utilizing these equations for A and B. But we know SE and we know the ultimate tensile strength. All we have to find now is F. So we will find F from our diagram. Here's the diagram we used. So we actually use this fatigue strength diagram to find the value of F. So the value of F is going to be related to the ultimate tensile strength. Our ultimate tensile strength is our ultimate tensile strength is 470 megapascals. So our F value is slightly off of the charts. So since it is off of the charts, we let F equals to 0.9. But if it was the other way around, we can approximate like around here. But since it is off of the charts, we let F equals 0.9 in this case. So if F equals 0.9, we can express that A we can express that A, wait, why is it not? Yes, that A is equals to 0 0.9 times SUT, which is 470 megapascals, and all that squared over SE, which is 175 megapascals. So then A is equal to 1,000 uh 22.5 megapascals, and B is equal to negative 1/3 log of 0 0.9 times 470 over 175, and this is equal to negative negative 0.127767. So then we can calculate that n is equal to or actually we cannot calculate n yet. We have to calculate sigma A and sigma m first. Sigma A, if you remember, is equal to let's look at the equation chart. So sigma A is equal to sigma max minus sigma min over 2, and sigma m is equal to sigma max plus sigma min divided by 2. Over here, we don't have a kf factor because uh we assume that kf is equal to 1, I think, because the q or the notch sensitivity uh like yes, I think that the notch sensitivity here does not exist because the notch radius is there isn't really a notch radius. So kf in this case is equal to 1, I believe. So that's why we simply apply sigma A equals sigma max minus sigma min over 2, and sigma m equals sigma max plus sigma min divided by 2. So I did some research about why we multiply by kf sometimes. And online it says that the multiplication of sigma A alternating stress and or sigma m, in other words, mean stress by kf, the fatigue stress concentration factor, has to do with accounting for the effect of geometric discontinuities like notches, fillets, keyways, or holes on fatigue behavior. Key definitions. Sigma A is alternating stress. It's a stress component that varies cyclically around a mean, and sigma m is the mean stress, which is the average stress over a cycle. KT is the theoretical stress concentration factor and is the ratio of max stress at a notch to nominal stress, which is purely geometry based. Um, so KF is the fatigue stress concentration factor and is the ratio of fatigue strength reduction due to a notch. It accounts for material sensitivity to notches. So why multiply sigma A or sigma m by kf? Sigma A times kf. This is always done when a notch or geometric discontinuity exists. Fatigue life is highly sensitive to cyclic stresses, especially in tension compression. So we amplify the nominal alternating stress by Kf to reflect the localized cyclic stress at the notch root. This is critical in fatigue analysis using methods like SN curves, which is the stress life method, modify Goodman, Gerber, or Soderberg diagrams. Multiply sigma A by Kf to reflect actual fatigue damage potential at stress risers. Sigma M times Kf. This is more situation dependent. Whether or not to multiply mean stress by Kf depends on the type of loading and the method used for life prediction. Consider the mean stress sigma M causes static loading effects. For ductile materials, mean stress is less sensitive to notches than alternating stress. Therefore, many engineers use Kf only for sigma A, but not sigma M. However, in some methods or conservative designs, sigma M is also multiplied by Kf, especially if the mean stress contributes significantly to crack initiation. If you're using a conservative modified Goodman diagram and want a safety margin, or the material is brittle, where static and cyclic strength are both sensitive to notches. Uh, yes, so there you have it. So in this problem, we don't multiply sigma A by Kf. There's no Kf factor here because there isn't really any discontinuities or notches that are mentioned explicitly. So we assume that there are none. But in our previous video, that I will link after this YouTube video, there's another video that we did where we had discontinuity, so we had to include Kf in that problem. For instance, in this example, we had to multiply by Kf because as you see, it says that in this example, there are fillets that are 1 over 16 inches in radius. So we had to apply a Kf factor this nominal stress uh, to this nominal stress. Nominal stress is just dependent on geometry. It is just like the normal axial stress, which is here calculated is from flexural stress. It's MC over I. The nominal stress is from the flexural stress, but here we had to multiply it by a Kf factor um, because of fillets. So that's all it means. Yeah, so luckily in this example, we don't need to consider Kf. But sigma A is sigma A, or we'll call it sigma A1 equals um absolute value of sigma max 1 uh yes, minus sigma min 1 over 2, and we take the absolute value of that. And it's equal to the absolute value of sigma max 1, which is 360, minus sigma min 1, which is 160, divided by 2. And that is equal to 100 megapascals. On the other hand, sigma m1 is equal to sigma max 1 plus sigma max, sorry, min 1 over 2, which is equal to 360 plus 160 over 2, which is equal to 260 megapascals. And now we can apply the Goodman equation, which is reverse stress is equal to sigma A over 1 minus sigma M over SUT to solve for the reverse stress first, that we will plug into the equation here to find the N. So sigma A R1, or the first reverse stress, is equal to sigma A1 over 1 minus sigma M1 over SUT, and it is equal to 100 over 1 minus 260 over SUT, which is 470 megapascals. And this is in turn equal to let me see. So 100 over, yes, it's equal to 223.8 megapascals. And since 223.8 megapascals is greater than the endurance limit of SE, SE is equal to 175 megapascals. Since our alternating stress 1 is greater than SE, this means it is finite life. Okay, so now we have our alternating stress 1, we can calculate N1. So N1, oops, N1 will be equal to the alternating stress 1 over A1. Actually, all these should really be A1, B1, and etc. A1 over 1 over 1 over B1 is equal to 223.8 over 1022.5 over 1 over negative 0.1277667, and this will give you 145,920 cycles. All right, so for our second loading, which is sigma A2, first of all, it's fine. Sigma A2 is equal to sigma max 2 minus sigma min 2 over 2, which is equal to 320 minus minus 200 minus minus 200 over 2, absolute value. When we get that equals 260 megapascals. Sigma M2 is equal to sigma sigma max. Yeah, sigma max 2 plus sigma min 2 over 2, which is equal to 320 minus 200 over 2. 320 minus 200 over 2, and that is equal to 60 MPa. And now we can calculate sigma AR to order completely reverse for the second loading, and that is equal to sigma A2 over 1 minus sigma M2 over the ultimate tensile stress. This is equal to 60 over 1 minus sorry, this is supposed to be a sigma A2, so it's supposed to be 260 over 1 minus 60 over 470. This is the ultimate tensile stress. And sigma AR2 is equal to 298.0 megapascals. Now we have to calculate N2. N2 is equal to, we're almost done, sigma AR2 over A2 to the power of 1 over B2. And let me see, both A1 and B1 are equal to A2 and B2 because A and B are only in terms of like the ultimate tensile strength and the fatigue and the endurance limit and F, which are all constant for the same material property. So we can simply plug in A1 for A2 and B1 for B2 over here. So equals sigma AR2 over A1 to the power of 1 over B1 is equal to 298 over 1022.5 to the power of negative 1 over 0.127767. And calculating that out, we have that it's equal to 15,520 cycles. For Miner's rule, we have in the beginning we had that N1 over N1 plus N2 over N2 equals 1. We had that N1 equals 8 times 10 to the 4 cycles. So 8 times 10 to the 4 cycles over N1, which is 145920 cycles, plus N2 over 15,520 cycles equals 1. And solving for N2, we have that N2 is equal to 7,000 cycles. And this one is our answer. So thank you guys so much for watching this video, and I hope this helped you guys understand this type of problem better with Miner's rule. And I'll be posting this slide with the solution afterwards, and have a good day.